Again, the joys of technology. We'll get there in the end. Okay. Just make sure everything's working. Okay, give me a hands up if you can hear and see me and you hear the PowerPoint. We'll just make sure. There's been a bit of technology wizardry going wrong, I think, this morning. Hands are going up, good. Okay. Good. Everybody sleep well? Everybody refreshed, ready for today? All good? Ready for some questions first thing? All is good. Yeah, as promised, as I finished yesterday, before we start the oil system, I shall go back through the fuel system from the fuel pump through the spill valves and other bits and bobs as well. Make sure we're happy. We're happy as can be anyway, especially with fuel pumps. Okay. All right then. Who wants to tell me what is the component that controls the pressure within the fuel pump and a variable displacement pump? Who's feeling confident straight away?
Governor, sir.
Anyone answer?
Governor, right?
Say again?
Governor, sir, I guess.
Not servo. It doesn't control the pressure. It's what is the component that controls the. If the pressure gets too, let's put it another way. If the pressure gets too much in the variable displacement fuel pump, what component in the fuel pump prevents it from over pressurizing? If that makes it easier.
Governor.
Yeah, good old governor. Yeah.
Speed governor, yeah.
Okay. So yeah, good old governor. So if the governor has to move, what does it move? Oh. Right, push back. So if the governor moves, what does it move, and what happens afterwards? Questions first thing in the morning, or well, for me anyway, for you guys this afternoon. So you should be nice and awake. Let's see. Who's wanting
Spill valve.
Spill valve, yeah. So it's going to open the spill valve. Then what will happen? So if it opens a spill valve, what's going to happen?
Pump output decrease, sir.
Yeah, pump out decreases because if we're spilling servo pressure. Okay, so if we're spilling servo pressure, then if servo pressure is decreasing, then pump output is also decreasing. In other words, the servo piston now moves back to inside the pump, which decreases the cam plate angle, which decreases pump output. Good. Okay, so normally if the pressure builds up too much in the pump, the governor can react and open the spill valve, which is good. What happens though if the governor has maybe a bit of damage to the diaphragm? So it's got a hole in the diaphragm for some reason. What would happen now if the pressure builds up? What would happen now if the governor fails? Because maybe got a hole in the diaphragm. So the pressure's building up.
It will create centrifugal force.
There is centrifugal force. That's part of the normal governor part, where the fuel's getting pushed out to increase the pressure in the pump. But what's going to happen? Normally, if the pressure builds up, it will push the diaphragm up. You know, looking at the diagram to open the spill valve. But what if there's a hole in that diaphragm and there's nothing to react against? So what could happen now?
Is it hunting?
Yeah, you'll get hunting. And what causes that?
Engine RPM.
Yeah. What makes it hunt though? Why is it hunting?
If RPM drops and centrifugal fuel pressure will reduce.
Yeah, but why is it going to reduce? I'll get out of here. You're right, though, it will reduce. But why is it going to reduce? And why is it going to increase again?
As the cam plate.
So normally the governor would push up to rotate the spill valve, okay? But let's pretend that the governor's broken. So what can move that spill valve instead of the governor? What is there always? I can't say it without giving the answer. What is there? There's always something there that will move the spill valve or allow the spill valve to open, even if the governor's broken.
Natural pressure controls or
No.
Plungers.
Say again.
Plungers.
No. Think about the spill valve and where it touches the servo line. Yeah. Does it always touch the servo line, or is there a little gap?
There is a gap.
Yeah, there's always a tiny little gap between the spill valve, the half ball valve, and the servo line, yeah? So if the governor fails, let's say there's a hole in the diaphragm, the little rubber diaphragm that moves up and down. The fuel can get through there, pressure builds up. The pressure can go between that little gap of the spill valve and the servo line. And that's enough to actually push the spill valve off the servo line, which will allow the servo line to decrease pressure and so decrease output. But eventually, what will happen is there's a little spring underneath that spill valve that will then push the spill valve back up to the servo line, so then increase pressure again, and then it will just keep going back and forward, back and forward, back and forward, which will give you your hunting. So it will decrease pressure for a little bit, then it'll increase pressure, then it'll decrease pressure, then it'll increase pressure, and that is your hunting of the engine going that sort of sound, up and down, up and down. Okay, but better that than exploding the fuel pump or overfueling the engine. Yeah. So what would happen if you get that situation as an engineer? You just pull the throttle back, and then you go investigate the governor or follow the procedure. Make sure there's no leaks and whatever. But there's a good chance the governor's being adjusted or replaced. Okay. If you're a pilot flying, yeah, you would just bring the throttle back to a safe RPM limit. You don't have to bring it all the way back because you'd be flying at maximum, and no way the pressure is going to build up too much if you're going to maybe maximum RPM or rapid throttle increase. So if you bring the throttle back, then it should sit there okay, unless there is a severe fault within the servo line itself. It could be things like the servo pistons may be stuck as well. You know, that could be pushing the cam plate fully out. There's maybe a leak somewhere in the pump. But again, if in doubt, bring the throttle back, and even if need be, shut the engine down. Okay. So that's just in case you get a governor fault. So the governor, 99% of the time, will make sure it's okay, but there's a little rubber diaphragm that goes up and down, so it might get a hole in it through wear and tear, or even the spring in the governor might break as well, so just be aware of that. So we spoke about spill valves. There's two types of spill valve. The first one we looked at there was a half ball valve. What's the other name for the other type of spill valve? So the half ball valve, and the other one is called the What's it called?
Knife edge.
Yeah, kinetic knife valve. Oh, yeah, knife edge or kinetic knife valve. That's the main one. Yeah, good. Okay. Now, if I said to you, if the knife is out, what position is the valve in? Is the valve open or closed?
Question again.
If the kinetic knife valve is out of the stream, is that the valve open or is that the valve closed?
Valve close.
Close.
Yeah, closed. It's not in the stream. The knife isn't in, so it's not cutting the stream, if that makes it easier to remember. It means it's not bleeding. So if it's not bleeding, it's not releasing pressure. So in other words, it's pushing the stream, the high pressure is pushing the piston over to the extreme. So it's closed position, so high pressure will be there. In other words, servo pressure is increased, so delivery, pump output will be increased. So likewise, if the knife is in, well, the knife's cutting through the fuel stream, so it's bleeding away. So that means it's open, so that means it's decreasing servo pressure, decreasing pump output. And if it's halfway in between, then it's stable, it's in neutral position. Right, on to changes in ambient conditions. We have got the spill valve attached to two capsules, if you remember from your diagram. One is an evacuated capsule, one is not an evacuated capsule. Which one is used for ram effect? If you remember the diagram, the top or the bottom one?
Bottom one.
Yeah, the bottom one. And if I was given that an annotation, P something, would it be P1 or P0?
P1.
P1, good. Intake pressure, yes, so that takes into account of the speed of the aircraft. So the faster that's going, the more air it's getting rammed into the intake, which will increase P1. And we can use the reference of P1 and P. Air that's getting pushed into the intake. Well, if we're getting more air pushed into intake, that means we need more fuel. So if we need more fuel, what position would the spill valve be in? Open or closed?
Close.
Close.
Yeah, it'll be closed. We've got to increase servo pressure, so we need to close the spill valve. So to close the spill valve using the P1 capsule, it's got to expand. Like a balloon, if you blow in a balloon, it expands. Well, intake, let's pretend that intake is the entry for the balloon. The more air going into the intake, the more that capsule is going to expand. But that will expand, that will close the servo valve. Servo valve pressure will increase, therefore pump output will also increase. So the top one, that's the evacuated capsule, so it's a sealed capsule. What was the other name for it again? It was called the evacuated capsule or?
Aneroid capsule.
Aneroid capsule, good, good, good. So same again, as we go in altitude, it's got sea level pressure inside it initially. So when we start going up in altitude, we go up in altitude, what's going to happen to the capsule? Will it expand or contract?
Expand with the altitude.
Yeah, so it's going to expand, and again, as it expands, it's going to push this bleed valve off the servo line, which is going to bleed the servo pressure and reduce servo pressure, therefore pump output will also reduce. So let's give you an example. Let's say I'm in the aircraft, I've got a fixed throttle, okay, but I'm going to put the nose down. I'm going to go in a dive, but keep the throttle the same position. I'm not going to move the throttle, I'm just going to pitch the aircraft into a dive, down the way, okay? What's going to happen with the spill valve? It's going to be a fixed speed, going to a dive, I'm going to keep the speed constant, but what's going to happen? What's going to move within that system? If I keep the speed constant, the throttle constant, but I'm going in a dive, I'm coming down the way, what's going to move?
Close.
Spill valve will be open.
Okay.
No, I think it will be close.
It's going to start to close, isn't it? Because we're coming from high altitude, we're now going down altitude. So what happens to air pressure as we come down in altitude?
High pressure.
Yeah, we're going to get high pressure. If we get high pressure, which capsule is going to move? In which way? Is it going to expand or contract?
Contract. Automatically expand, is it?
Yeah, it's going to contract. So the P01 is going to contract, which means it's going to shrink, which means it'll lift the servo line up, which will close the servo line, and then will increase servo pressure to increase fuel. Increase fuel output to stabilize depending on the RPM. Because we have more air, that means we need more fuel, to match the mixture, okay? Until we actually move the throttle as well. So that maintains the mixture. And that's the ideal. Yeah, if you come in dive, you'll probably get faster and faster. So to be honest, as you come in dive, you'll probably start speeding up. But theoretically, if you could keep the speeds constant using drag, fixed throttle setting, in theory, it would just be the P0 capsule. But as you're speeding up coming down, then the P1 capsule, the bottom capsule, it will also try to increase or expand sort of thing, which will, again, try to open. So between the two of them, they will get to a certain point where they will have the right gap, which is restraining the servo pressure line to increase fuel appropriate to the air it is required. Okay. Right, with the pressure differential line, if we've got high pressure upstream, okay, what's going to happen to the spill valve? If we've got high pressure upstream, so we've got high pressure in the upstream line for the differential spill control. What's going to happen? Will spill valve
Open.
Say again?
It will close the spill valve.
If it's high pressure,
It will open.
it's going to open. Yeah, that's to be the same as having engine at high RPM and then pulling the throttle back quickly, where you're going to get a back pressure. So that back pressure will be felt in the high pressure line, and the little sensing line from the high pressure line goes up and over the top of the spring, which pushes down on the spring, which opens the spill valve, which decreases the fuel output. If you open the throttle, then you open a hole, so that'll let some pressure off in the high pressure line initially. Well, that will allow the spring to push the valve up on the spill valve to close the servo pressure to increase servo pressure to increase output. Okay, so just all it's sensing is the differential between upstream and downstream of the throttle. Okay, so if you get a high pressure upstream, that means you probably close the throttle from whatever setting you've had. Okay, if you get a low pressure upstream, you've probably opened the throttle waiting for the fuel system to respond. In other words, you need to close the servo line. Okay. What was the name of the throttle assembly? It has a throttle within a throttle. So the normal throttle is just at one control valve back and forward, but this other type of throttle, what was that called? Dashpot throttle, good. Okay, yeah, have a read over the dashpot throttle. I think it's in your old books as well, if I remember right. Have a read over it, but again, it's just a control within a control. Okay, the opening will only open proportionally to depend what's on the pressure in the system, depend what's on the pressure on the throttle control, depend what's the pressure on the servo controls. It's like, I call it a shock absorber for a fuel control system. Okay, a nice smooth delivery compared to an open one. Okay, so we've got the pressure drop control diaphragm, we've got the evacuated capsule, we've got, which is P0, we've got the open capsule P1, all controlling the bleed valve, the spill valve. What other type of component will operate a spill valve? And it will operate on two types, or two options. So what else can operate a spill valve? I'll give you clues to do with electric. Might need two signals. What would
Solenoid.
Yeah. Yeah, it'll be a solenoid, and it'll get a signal from two sensors, which are
From amplifier?
the what one, sorry?
From amplifier?
No,
It will be from low pressure speed limiter.
yeah, low pressure, yeah, the LP spool speed, yeah, when that gets too fast.
And the
Okay,
gas
that-
pressure.
yeah, and the gas temperature, yeah, EGT, yeah. So if you get too fast or too hot, it will give an electrical signal through an amplifier. Amplifier will give the pulse to the solenoid, activate the solenoid, and that will also open a spill valve. Okay. Good. That's just a basic system, All right. Okay, doke. Right, we'll leave that for now. That's the bit I was just want to cover this morning. We're now going to move on to the oil system, the lubrication system. So I'll just put it up on the screen. That's good though. Good answers there. Just keep it up like that. See, it's easy peasy, isn't it? It's all dead easy.
Easy peasy.
Easy peasy lemon squeezy, yeah. Right, let's move on. Let's take a wet whistle. Okay, right, so we'll move on to the oil system. Now, we've looked at the fuel system, so now we're going to look at purely the oil system. We've got those compressors, we've got turbines, we've got the shafts. Well, those shafts have bearings, and we need to lubricate those bearings with oil using some sort of system. Now, just on that diagram there, it's a good one just to recap a little bit there. We've got the external gearbox, okay, which is connected to your engine. There'll be a shaft which goes through what's called a bevel gear, like we did before, and that shaft will go up to the shaft of the spool. Now, looking at that spool, what shaft would that be? Would that be LP or HP?
LP.
Sometimes it would be the LP one, because that's too big a spool, because it's got a big fan in front, big turbine. So we always turn the small spool. So which one do you think it would be? Now that's actually a triple spool engine there, but if you can just have a look where it's connected here. So you've got a gear here, and a gear there. That's attached to this compressor. And so
It will be a high pressure.
Always a high pressure, yeah. There's your intermediate, and then the BLP here as well, yeah. So it'll be always a high-speed gearbox, high-pressure spool. The high-pressure spool is the smallest one, and that's the one that spins fastest because it's smaller. And then when the engine starts, the gas will come out of that one, and then go into the IP, and then to the LP in the end as well. So the gas moves it. So it's always the HP one, the smallest shaft. So it's a nice little example to show you. I might use that diagram actually when we do the spools anyway. But in the gearbox, you have lots of gears, you've got lots of moving bits. You'll have your starter motors attached to it, you'll have alternators, you'll have your fuel pumps, your RPM gauge, your tachogeny, all these getting driven. Well, if there's no oil in there, they won't drive for very much. So we're going to look at the oil system, oil pumps, and how we get the oil to all the bearings and all the rotating parts in there, and how we control that oil. So oil system, as said, lubricate and make sure it's fed with the correct oil, nice clean oil, and the right viscosity and that sort of thing. So lubrication system has to do what? Well, it's got to lubricate. It's got to keep the hot components cool. So as well as lubricating, that oil helps keep things cool. So if you go back to the FCOC, the fuel cooled oil cooler, remember the fuel helps cool the oil. And so when the oil is going round and round and round the system, when it goes to the fuel cooled oil cooler, it gets cooled down a little bit before it goes back into the bearings. Oil is very good at preventing corrosion. Remember, there's going to be moisture possibly in there because there'll be a lot of air in the gearbox. If you've got air, that means you've got water or moisture in the system. So again, that helps prevent corrosion, providing it's moving round. If it's not moving round, then obviously oil will start to drain down, leaving some components exposed, and that can potentially lead to rust. So in other words, resist oxidation at high temperatures. Oxidation is when we pretty much cook the oil. A lot of figures to remember, but we'll chat later on. When oil gets to about 124 degrees C, it oxidizes. Basically, it cooks. Okay, it's too hot. And the molecules in there will expand to such a point, it's not going to do its job anymore. It must possess suitable viscosity. over the full temperature range. Now we can start an engine at -40 and we go up to high temperatures, but the oil has to be able to cope with those extreme temperatures, hot and cold. So the viscosity is resistant to flow. So if an oil gets cold, it gets thicker, and as it gets hotter, it gets thinner. So it's got to cover the whole operating range for the engine, irrespective of the temperature, up to the normal operating temperatures. So the types of oil system we're going to look at 3 common types of oil system, and this one is pressure relief. Look at its full flow, and the last one's total loss. Now I've put the 2 in red because they're both the same sort of type. In other words, the class does 2 basic recirculatory oil systems. Okay, in other words, they use the same oil, they send it out, and it comes back to the tank. But they do it 2 different ways. Although they're quite similar, they do it 2 different ways. And the last one, the total loss, is as it sounds. It loses the oil. That's for the older military type aircraft, but we'll mention it anyway. The 2 ones you might be concerned with are the pressure relief and the full flow. Normally, if I was there in the classroom, I would get you to draw the oil systems once we've gone through it, so we can't do that at the moment, but we'll have a bit of fun with that, I'm sure. So pressure relief one, pressure relief system, oil flow to the bearing chambers is controlled by limiting the pressure in the actual feed line to a given design value. Okay. Now, as it sounds, pressure relief, if the pressure gets too much, there'll be a pressure relief valve in there which relieves the pressure back to the tank system. Okay, so it doesn't get too much. As you can see there, in this diagram, we've got the orange sort of colour, the feed oil, and the green is return oil, and the white sort of breather oil air mist, because you always have a bit of air in there. And you've also got maybe a torque meter. This is actually a turboprop engine. Okay, you can see here, this will be where the propeller goes on. So you can actually use some of the oil for a torque meter. Still a gas turbine engine, but just got a propeller stuck on the end of it. So if you look at, there's the gearbox. Okay, in here you'll have an oil pump. You can just see where my laser is there. Okay, that will help pump the oil around the system. Again, you'll see where it's going all the way around, up to pressure relief valves. There's bearings here. You can just see there's another bearing, some gears, bearings, and again some bearings at the back as well. Okay, and that's its purpose, to go and cool those bearings, lubricate those bearings, and then once it's done its job, it will go back down to the tank as well. And we'll mention some parts that were within the tank as well. That's a basic pressure relief one. In there you'll have your bearing chamber pressure, pressure difference, augment spring pressures, some components in there, maintains constant supply, and this is what the actual system looks like. A basic layout of a pressure relief system. So let's look at the top. So we start off with a tank. We need somewhere to hold that oil. And there are a few more components in the tank, but for the moment we'll just look at the basic component setup. Now we've highlighted the pressure line as red, the scavenge line or return line is in green, and the vent line for air is in blue. All right, so we've got a tank, so we go down and we've got a pump, some sort of pressure pump. Now the type of gears in the pressure pump will be standard spur gears. Okay, standard. We don't need a variable displacement one. We just need a typical spur gear pump. Okay. It will run proportional to the engine RPM. For the pump itself, we might need a relief valve for the pump. Okay, just in case we get a bit of back pressure, the relief valve can operate and that will put it back to tank as well. So we've got a few more relief valves. Then we've got the fuel cooled oil cooler. So the fuel will be coming in, going through the matrix, oil will be going around the matrix, so the fuel is keeping the oil cool. And as the warm oil gets warmer, that helps warm the fuel up. And again, there will be a bypass valve there for the oil. Okay, so if the oil gets too thick, too cold, at least it can bypass the cooler initially to help move on to the actual bearings. Okay. Then you have what's called a PMV, a pressure maintaining valve. So just making sure the pressure is staying correctly in the high pressure side. I meant to say, in the tank you also have a filter, a little low pressure filter. Then we get to what's called the high pressure filter. Very small grains of filter material, just in case there's a little bit of debris from between the FCOC or the PMV or in the line itself. Okay. And again, there will be a bypass valve there for that as well. So not always, but usually you better have some oil than no oil. Better have some dirty oil than no oil at all. Okay, so if that was to become blocked, for whatever reason, then we can bypass oil and at least have some sort of oil than nothing at all. Then the last bit will be, we will get to the bearings. Now in the high pressure line, all right, from the tank to just before the bearings itself, you will have your system pressure relief valve. Hence why it's called a pressure relief valve oil system. So if the whole system gets too much pressure, pressure relief valve will open and relieve excess pressure back to tank until it stabilizes. Okay, but when it's working properly, oil will go to the bearings, front, middle, rear, wherever. Okay, and then once it's gone through the bearings, it will then go back to tank down this green line here, which is the scavenge line. Now in the scavenge line or the return line, we also have a scavenge filter. Now this filter is not as thin or as small as the high pressure one. It's just there in case something maybe has come off, a seal or any bits of debris, and we can use that for diagnostics because the oil has been used in this part. If it's been used, it might have information for us that why is something breaking down. Well, we can use that filter for diagnostics. Now, in the low pressure side, the scavenge pressure is a low pressure. There's not a lot of high pressure. There shouldn't be any pressure there at all, or very minimal. So what we do, we have an extra pump to help that return oil go back to tank. And you tend to find that the return pump has got bigger gears compared to the high pressure pump. Now, they're not two separate pumps. They're all in the same housing, but they're doing two different jobs. You've got inside the housing, one set of gears is a high pressure, and the other set of gears is the low pressure of the return line. And even from the diagram, you see that these gears are bigger than the high pressure. Why do you think we'll have bigger gears on a return pump compared to the pressure pump? Anybody? Why do you think that would be?
Question, sir, again.
So we've got a return pump on the low pressure side because the green line is the oil going back to tanks. There should be no pressure in there at all, or very little. But we've got a bigger pump compared to high pressure. So why is the high pressure pump smaller than the return pump? Why has the return pump got bigger gears in it? Why do you think it's going to be bigger? If it's the same oil, why have we got a bigger pump?
It might be for cooling.
Not for cooling. The opposite of cooling. What's happened to the oil as it's gone through the bearings? Has it got hotter or cooler? What do you think? As the oil comes out the pressure line, it'll be the same sort of temperature, but as it goes through the bearings, what's going to happen? Will it heat up or will it cool down?
Heat up.
Heat up.
It's going to heat up. Now, if you heat anything, what happens to you if you heat anything? It expands. Yes,
Expands,
so
yeah.
we've got a greater volume of oil. It's the same oil. It's not the same pressure because there's no pump behind it. It's just going back. But the volume has got more because it's expanded. So to cope with that extra volume of oil, we have the bigger size gear pumps. Okay, so you tend to find on the return line, the scavenge line, that the oil pump gears are bigger. I meant to take some photographs to show you inside the pump. They're all in line. You'll have, excuse me, the outputs are separated so they can't mix. But the pump gears, if you look inside the pump, you see small spur gears on one side, excuse me, small spur gears on one side and larger pump gears on the other side. So you can tell straight away which one is the high pressure one and which one is the low pressure. And the low pressure ones are bigger, which means it must be the scavenge pump. Scavenging away helps return the oil back to tank, okay? Because of the larger volume, that's all it is. Now, also in there, you can see after the pump, we've got what's called a magnetic chip detector. It's a magnet that goes inside the pipe, a little bayonet connection, and as the oil passes over it, if there's any bits of debris, of metallic debris, the magnet will pick those up and you will take these magnetic chips out at specific hours. We'll speak about those later, but just for now, just be aware of where they are. Okay. So, quick recap: read the tank, read the pump with the relief valve for the pump, then a fuel-cooled oil cooler to help cool the oil and to warm the fuel, and again, they'll have an oil bypass there. Then a pressure maintaining valve to maintain the pressure within the system, and a bypass for the filter, and then the whole system itself will have a system relief valve. In hydraulics, system relief valves tend to be about 10% above system pressure. You'll pretty much find the system relief valve is constantly open and it's maintaining in conjunction with the pressure maintaining valve. Then eventually it'll go to the bearing, depending however many bearings there are in that engine. And the magnetic chip detector, well, there will also be as many chip detectors as required. You can have one for each bearing. You have front bearing, middle bearing, rear bearing, centre bearing, intermediate bearing, like we had on the engine I used to work on. Or it might just be two, it might be a high pressure gearbox, it might be a low pressure gearbox. It all depends on the engine. All right, so that's the oil side. Now, we've got on the left hand side here, the blue line, the air line. Well, we've got air line. Why have we got air and oil? Well, as it goes through, when you fill an oil tank up, there's always going to be a little bit of air in there, and you will always have, like fuel, a little bit of air in the oil system through heating it and moisture, evaporation. So as the oil goes through the bearings, okay, it will then go back to gearbox and pump, etc., and we'll have what's called a centrifugal breather. Now, what that does, as the oil goes through there, it's basically like a pump. It spins really fast, okay, round and round. So the heavy oil goes to the side of the pump or the breather, and then drips back down to tank again. The air, which is lighter, just goes out a vent to atmosphere. Okay, so some of it will go back to atmosphere, and some of that will go. The oil will drip back to tank. Okay, so that's what's called a centrifugal breather. It just gets rid of the oil that's in the air system, and then puts the remaining oil back to tank. If you look underneath an engine, you'll see a lot of mist coming out the bottom. Okay, that's the engine breathing the oil system. You just see a little mist of oil. You will always lose a little bit of oil. You don't get all the oil, unfortunately. So eventually the oil level in your tank will start to go down. Okay, it's just standard, because you always get a few droplets of oil coming out. With diagnostics, you can also use that to check for drips. If you see a lot of drips coming out the breather, you can check your manual and it will tell you, for example, you may be allowed 3 drips a minute. If it's going drip, 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 then there's maybe a problem with that breather or the oil system you have to investigate. So you can use that as well for diagnostics. Why is my engine using lots of oil? But there's lots of things, but for the moment, just be aware of what it is. Okay, so that's just a very basic oil system for a pressure relief. Now it's classed, as I say, as fully recirculatory. In other words, the oil goes in, it goes round, and then it comes back again. Okay, so it's keeping the same oil. Yes, you will lose a little bit through atmosphere, but that's just natural. But it's classed as a fully recirculated oil level, and you just have to keep topping this up every so often. All right, and again with the pumps, small pump, high pressure, large pump for the return. Okay. Checking there. All right. Okay. Any problems with that one? Any questions? Yeah, it's all good. Centrifugal breather, yeah. It's just it's attached to the gearbox, inside the gearbox, and it's open to atmosphere. So as the oil comes into there, when it's been used from the bearings, it will spin, because you have gearbox oil. It will spin really fast. So the centrifugal force will throw the oil to the side walls, and that will drip back into the gearbox. But in the middle, the air is lighter, so the air escapes out to atmosphere. And that oil that's hit the walls and go back at the gearbox, again, will just go back to tank as normal. Okay? It's hence why it's called a centrifugal breather. Centrifugal action, as it's spinning really fast, throwing the oil to the side, oil drips back down, back into the return line, back to the tank to get used again. But you will lose a little bit of oil to atmosphere as normal. That's just normal. Okay, so that's a basic pressure relief valve oil system. Okay, right, what we'll do before we move on to the next one, it's very similar. There's only about 3 different changes on the next one. What's the time is that? We'll go for a break now. Come back in about 20 minutes again, and we'll go on to the full flow system. And I want to see what the changes are. It's very, very similar. Oh, excuse me. But there's only about 3 changes in it. Okay, I've got gas in my stomach here. All right, so let's go for a break for the moment, and come back in about 20 minutes. Okay, set by manufacturer, but very simple idea. What can happen through time if the oil has got some debris for whatever reason, the filter hasn't caught it, or the ball has stuck, or the spring is jammed, or whatever? Then yes, that could stay there and potentially damage the system. Okay, but usually something will blow off some point. They're usually pretty reliable most of the time. So that's your pressure relief valve system. Next, we're going to move on to is the full flow. Very, very similar. There's not much changes to it, except there's no pressure relief valve in the system. What instead we have is calibrated jets that are calibrated for the pump output, proportional again to the speed of the engine. So full flow system, you've got what's called a metered spillback, which it's always open, and the calibrated, as I say, for the type of system that is there. So the oil jets are also calibrated to the pump output. You'll have a pressure bypass as normal. You'll have pressure limiting valves, cold starting blockage components, and essentially, which you want to remember here, is a pressure differential switch, which will give you a flight deck 1. We'll show you that in a minute. So looking at the full flow system, not much difference, is there? It looks very, very similar. Yeah. So what we've still got a tank, we've still got a pump, we still have a relief valve for the pump, we still have an FCOC with a bypass valve there for the oil, we still have a pressure maintaining valve, which I'll speak more about that in a minute. We still have a high pressure valve, but in this time, where there was a pressure relief valve for the system, we don't have that anymore. What we have instead is a pressure differential switch, which changes the pressure upstream and downstream in the high pressure system. And if that gets too low, then a warning light in the cockpit will come on to let the pilot know that there's something wrong with the oil system. Once the oil goes through the bearings, as usual, it goes down the return line, back to scavenge line, back through your scavenge filter again back through your scavenge pump, and again back through a relevant magnetic chip detector and back to tank. Again, we've still got the centrifugal breather, again, which dissipates the oil back to tank and also gets rid of the air. But this time, because we don't have a pressure relief valve in the system, we've got this metered spillback, which is calibrated back to tank. So really, all we've got different is a meter spillback, excuse me, and a pressure differential switch. There's not much else different to that compared to the pressure relief valve. Pressure relief valve system, as it sounds, if the pressure gets too much, a pressure relief valve opens. Where this system doesn't have it, it has a pressure differential switch, a warning light in the cockpit, and a metered spillback. 3 different things. That's all there is to it. Okay. So normally what I would get if I was in the class with you, we'd go through this a few times, and then get you to come out the classroom one at a time and draw each component one at a time on the board, and we actually build up an oil system. Okay, bit of a fun, but can't do it on here at the moment, but we'll speak a bit more about it. Now, both systems, as mentioned, they've got a pressure maintaining valve. Okay, now, the pressure maintaining valve, as well as maintaining pressure, it helps maintain the pressure in the FCOC for the oil. And the reason it does that is we make sure that in the FCOC you've got oil and fuel. Now, if something breaks down in there, there's a chance you can mix the oil with the fuel, which is not a good situation to happen. There's 2 ways that can go. The oil can mix with the fuel and go into the fuel system, or the fuel can mix with the oil and go into the oil system. Which way is the worst way? None of them are good, but which is the worst out of those 2? Oil into the fuel or fuel into the oil system?
Fuel into the oil system.
Yeah, fuel into oil system, because if fuel goes into oil, it's going to thin out the oil. It's going to make it more viscous. Okay, it's going to be very, very runny. Less viscous, sorry. make it very, very runny. Now, if you've got runny oil or very thin oil, and that goes to the bearings, well, it's not going to do its job. It's not going to lubricate, it's not going to cool, and if you've got fuel and oil going to very hot bearings, you've got potentially for an internal engine fire. Again, not good. So what the pressure maintaining valve does, it ensures that the oil pressure in the FCOC is always higher than the pressure of the fuel. Okay, that way, if the oil goes into the fuel system, well, not ideal, but it's better than the fuel going to oil, because if oil goes into fuel, where does the fuel go? It goes to the burners, it gets burnt out and goes to exhaust. Yes, you'll have a smoky exhaust, but we can live with that for short term to sort the problem out. But if you get oil in the fuel and goes to the bearings, then that's a lot different. Okay, so the PMV, the pressure maintaining valve, always ensures that the oil pressure in an FCOC is always at a higher pressure than the fuel, and that goes for both systems. Okay. All right, so there we go. There's your partial loss. We used to call it partial loss back in the military days. The pressure leaf and the full flow system. And there they are both together. So as you can see, not very dissimilar to each other. As I say, the full flow has the meter spill back, whereas in the pressure leaf, we've got the system leaf valve. So where the pressure leaf was, we now have a pressure differential switch, which goes to a light in the cockpit. Okay. And apart from that, there's not much difference to it. They both have centrifugal breathers. They both have high pressure filters. They both have scavenge filters. Now, scavenge filter is a larger mesh of wire. It's only for bigger bits of debris, possibly maybe a bearing's broken down as it's being used and things like that. Again, you can use that for diagnostics. Okay, and FCC is still the same. The pump is still the same. The tank is still the same. And we'll look at bits and pieces within the tank as we move on. Okay, so there's both systems side by side. Total loss is as it sounds, only for short purposes only. This is old military type aircraft where it's basically like a one-shot system. Oil will get used, and eventually, once it's been used, it'll go into exhaust and get spun out the back end. Okay, it's just a one-shot system. So you have to keep filling every time it lands. You have to keep filling it up. Old type system, not very good for the environment, not very environmentally friendly to say. So a single-shot pump which constantly squeezes oil out until you eventually run out. Okay, and that's a base. I'm not going to speak too much about that one. It's just a total loss system. Okay, not much to that one then. Classed, or commonly known as a single shot. It goes flying and it lands before it runs out of oil. That's as simple as it. Very basic old system. So class is expendable, short periods only. There's no cooler required. No scavenge pumps because there's no return line. No return pipes, hence why there's no scavenge pumps. There we go. Okay, so very, very basic system. Nothing too much to worry about there. Oil tank though. So in the tank itself, what we're going to have? Well, we're going to have oil, definitely. How much oil do we have? Well, we need some method of ensuring how much oil is in there. Now you have various different methods. On this one, we'll start over here. We've got a sight glass, just a little window. What will be calibrated lines down the window, so it's a visual. You can tell straight away how much oil is in that tank just by a little air bubble at the top, because you always have air. If you can't see an air bubble, you're either too full or it's completely empty. I'll give you a little example. Many years ago, when I was just a junior, we went down to recover an aircraft from a place in England, and we replaced the engine. Everybody's experienced. Now, the sight glass in this oil tank here is very similar to one we used to have. On the left engine, it would be an outboard side. So you'd open the door, it's there, nice and easy to see. But the engine we changed was on the right-hand side. Now, the engines are orientated the same way. So the oil tank on the right-hand side was actually inboard to the fuselage. So when you're looking up, there was not much of a gap to see it. Every single one of us put a torch up to check the level. And we all thought it was full. What it was the dirty sight glass. So when we shine a torch there, we thought that bit there was full. Well, went to start the engine, and lo and behold, the differential light came on, low oil pressure. So we checked it again. Yeah, there's definitely oil in it. We even changed the sensor. We thought maybe a faulty sensor on the new engine. Changed that, same again. And eventually I went back out and I undid the filling bayonet connection, pushed it up, and guess what? No oil came out. It was empty. But because we got it quick enough, we filled up, the actual engine was okay. It's not a problem. But just because the sight glass wasn't very easy to see, and it was quite a dirty glass, it looked like the oil tank was actually full. We thought somebody had filled it up. It just shows you communication. Engine oil is very clear. So if you put brand new oil in, it's very hard to see it sometimes. And once it gets used, the colour will change, it will get a bit darker, it makes it a bit easier to see. So that's why it made it a bit awkward initially. But again, if you overfill an oil tank as well, that can cause problems. That can cause siphoning effects. So make sure, depending on the aircraft you're working on, it will tell you only top the oil up when it's hot, maybe after 5 minutes of engine cool down. You should never really fill jet engine aircraft oil up when it's cold, because it's contracted. If you fill up to maximum when it's cold, when it expands, it can potentially blow the tank or siphon the oil out. Now, some aircraft are okay with that, but most jet engines, you only top the oil up maybe a few minutes after the engine has landed, or the aircraft has landed. But again, check with your maintenance manual. Other types of way of checking oil, you might have a drop stick. Okay, we actually put a lever, a little dipstick into your tank, like cars and motorbikes. The opposite of that is what's called a drop stick, where actually underneath the oil tank, you unscrew it, it pops out, and it has a little magnet on it, and there'll be a little float inside the oil system that when you put your stick in there, it will stick to the magnet, and then you read off the calibrations on there. Some new ones are also just fibre optic, so you shine a torch in, and it will shine on LEDs to show you the level as well. So it all depends, but most are mechanical type, either a visual sight glass like that one, or a drop stick, or a dipstick. Okay, various types in that. At the top of the tank inside, you'll have what's called a deaerator tray. And as it sounds, it gets rid of the air and the oil as well. So the oil will be splashing around, oil will, and the air mixture will go in this deaerator tray. Very, very, you can just about see it, maybe hard to see here. There's very, very fine holes. The oil will drip through the holes eventually, and the air will just sort of float up, and then that will go out through a vent valve in the tank. On the side of that, you might have the oil pressure transmitter, let you know the pressure that's actually on the tank. You might have a pressure switch, which will just come on or off if the oil pressure is low. Your pressure filler, yeah, you have a connection, so you can actually plug in your oil ris bridger to pump the oil in. Most jet engines, as you pump the oil in, you don't just pour it in. Older engines like piston, yes, you just pour the oil in, but on jet engines you tend to connect it. There's a spring-loaded valve. We use a little ridge bridge and pump the oil in. And you'll have your scavenge lines, you'll have strainers, so strainers, a feed to the actual pressure pump, and you can see there's a drain to drain the engine oil out of the actual tank. And attached to the tank, you might have a filter assembly attached. So although in the diagram it shows it all over the place, actually it can be quite compact, very close to each other. High pressure pipes tend to be smaller, and your return scavenge pipes tend to be bigger, hence the bigger pump. Okay, and there we go, there's a system relief valve. So again, it's all quite close. So in the schematic, it shows you, as I say, quite far away, but actually in real world, it's actually very close together. It might even be attached to the same thing. The pump could be very close to the tank. All right. Filter bypass, there we go. There's another oil from the cooler, and also some have a drain for the filter as well. Okay, so that's a basic sort of setup. So in red, there's your high pressure feed oil. The green oil is the return, and then the white here, it would be your air and oil mist. Okay, and that's a basic tank. They all do vary, obviously, but they pretty much do the same job. Filters, you'll have a low pressure filter and a high pressure filter. A low pressure filter tends to be a wider gauze, just initially grabs the big bits of debris that can potentially in the tank. And then you have a high pressure filter, which would be finer gauze. Now, usually you might have they're all sort of a wire gauze, so you can actually clean these. You can put these in an ultrasonic bath. For you guys, you'll just go to stores, you get a set of clean ones, you take the old one out, and it will go away with the paper as well. If you drain the oil out, you're going to get checked, because they'll wash it out, make sure there's any debris. And likewise, when you take a filter out, have a look at it. is there anything on there? You'll learn through time what's normal. If you open it up and you see something orange or black or red on there that's not normal, it could be a seal, it could be indicative of something else that's maybe it shouldn't be there. If in doubt, get it checked out. Okay. So these are the high pressure ones. They can be reused. Some have a wire mesh support and some with a fibre. Unlike the fuel ones are pretty much once use only, but certainly these can be washed in an ultrasonic bath where it vibrates them very quickly at high frequency for about 3 minutes, and then they clean off with a solvent, and they get reused again. They might even have serial numbers for traceability for problems with engines. And then we have what's called a last chance filter. Now, last chance filter is a very small filter, only about that sort of size, a very, very fine mesh, and it's called the last chance because it is the last form of defense before the oil goes here to the actual bearings. Now, you can only change these really when the engine goes for refurbishment or stripped down in an engine bay. Again, you can use them for diagnostics as well. It's a thread type where you screw it in to the housing just before the bearing. There's your oil feed as it goes through this very fine mesh, and then so that's the last chance, hence the last chance filter, just in case there's a small amount of debris that might have gotten past at something for whatever reason. And the last thing you want is even the smallest grain of dirt on a high-speed bearing is going to cause a bit of damage. So this little filter can prevent that from happening. Okay, so that's your main sort of filters there. Magnetic chip detectors was briefly mentioned. Again, there's a simple fit. They are push fit. You've got a valve which has a spring behind it which seals when the chip is out. But as you push the chip in, it opens the valve and you lock it in position by what's called a bayonet fix. Yeah, these little pins, you push in, you twist it, pull it back, and it locks in position. The important thing there is make sure when you push it in and twist it to clockwise, you pull it back because they can stick. If you stick in the open position, you can lose oil very, very, very quickly. So in, twist about 90 degrees, pull back till you hear the click, job done. They're not very big, they're about that sort of size. They do come in various sizes. And all it is a housing with a couple of seals and a magnet on the tip. So any oil going past the tube with any debris, metallic debris, that will get picked up on it. And again, through experience, when you take these out at predetermined times, you will, yeah, that looks normal, but occasionally you might take one out and went, wait a minute, that doesn't look right. These all get tested in what's called an Early Fail Detection Centre, or EFDC. Again, I used to work in one of these. We put the debris under a microscope initially to have a visual check, and then we put it into an electronic microscope that goes down right into extreme detail, and it can actually diagnose and tell you exactly what that material is, what type of metal. Is it metal from the bearing itself? Is it metal from the bearing cage? Is it metal from the housing? And we use it as a form of preventative maintenance, where these will take out every so many hours, and if everyone's fine, they'll just get changed every time. If we start to see a buildup of debris that's getting a bit more and more each time, we'll reduce the amount of hours that you inspect it. So let's say, example, my aircraft used to work on, one of these would come out every 36 hours. If we saw a buildup of debris, we'd change it down to 18 hours, so it'd come a bit quicker. If it was getting worse again, we'd take it down to maybe 10 hours and 5 hours, and eventually say, no, that's enough now. We need to pull the engine. That bearing is breaking down far too much. So we keep the engine as long as possible, but we keep an eye on it. We keep a trend analysis so you can check if the system's starting to break down. So it helps prevent diagnostics. Again, going back to cars and motorbikes, you'll have a drain plug on your oil tank underneath the engine. And a lot of new cars nowadays will have a magnet on there. And not for diagnostics, well, it does help, but any little bits of debris, it stops those little bits of metallic debris swimming around the bearings on your engine. And a lot of cars are doing that now as well, which is quite a good idea. Okay, that's a basic one. Things you have to check for when you fit these is make sure the little pins here, grab them with a nail, make sure they don't come out. And even the magnets, some of the magnets are pushed fit in, sometimes they fall out. So again, just a little gentle feel, make sure they're okay. And ensure they have 2 seals fitted. You will get a new set of plugs from the stores, and they will be painted as well, because some engines might have 1 or 2, some engines might have 5, blue, reds, greens, whites, yellows, and that sort of thing. So make sure you put the same colour plug back into the same position when you place it. So do one at a time, take the green one out, you get a green plug, put the green one back in. The reason they're colour coded, because they will be colour coded for front bearing, rear bearing, intermediate bearing, and so on and so on. So if you get them mixed up, that can give false information to diagnostics and cause a lot of problems. So make sure, take your time, change them one at a time. Okay, and that's a basic magnetic chip detector, or NDP, so magnetic detector particle. And there it is. There's the system. You've got oil flow, some bits of metallic debris, and it will get picked up by the magnet. Again, they do vary in shape and size. Some are triangles, some are round for maybe single power systems, some are triangle for engine systems, some are just round in general. You know, it just depends on the engine type, but they usually are color coded. You're checking these as well. You'll have a bit of paper to write down the date, the time, the engine hours, the aircraft it came from, and that sort of thing. So you need a bit of information when you change these as well. A fuzz burner, you'll find these, certainly some modern aircraft, but definitely on helicopter type aircraft, is when the magnet picks up some metal, when it comes up too much, it will make a contact. That'll make an electrical signal. That'll give a warning in the cockpit, especially in helicopters, that there's debris in the system. Now, it's very crucial. Obviously, on an aircraft, you might have 4 engines. Well, if you lose one engine, that's bad. At least you've got another 3. If you lose an engine or a gearbox, if it's a gearbox chip, a gearbox in a helicopter, very, very crucial. Okay, if they start going wrong, you're going to lose all sorts of problems and actually potentially come down. So this fuzz burner, as the debris builds up, it's metallic obviously. Once it hits the sides, once a certain amount is on the magnet, it makes a circuit, gives a warning to the cockpit, and what can happen, it might just be, it's maybe had a heavy flying, it's maybe a lot of debris flowing about, it's not actually too bad. The pilot can press a button and actually burn it away, hence it's called a fuzz burner. So it actually burns the debris away. If it comes back very quickly, that's a good indication there's a lot of debris in the system. If he presses the fuzz burner button and it goes away, it doesn't come back, it could just be a little one-off. It could just be a little bit of debris. It's been floating about the system, nothing too much to worry about. But if it comes back very quickly, there's a good chance something's starting to break down very quickly and suggests the pilot needs to come down quite quick. Okay. An example of what we've seen happen once before, unfortunately, there was a helicopter in the North Sea for the offshore oil workers, and there was a known fault. They pulled the chip, a bit of debris on it. Now, what should happen is when a chip is pulled to be checked, that aircraft shouldn't fly until the chip has been tested. But as what usually happens is, as long as it's got a trend analysis on, they'll let the aircraft fly, and as long as it's within limits, they'll let it fly before it's been tested. Not ideal. What happened to the helicopter in this case? They pulled the chip. They found a big bit of chip on it, you know, a bit of tooth of a gearbox. What they should have done is gone and ground on that again, actually on the ground, and tested it again, and that would have brought up some more debris. Unfortunately, what happened is they let the helicopter go flying before they tested the chip the next time. Helicopter went flying towards the oil rig, lost its gearbox, the helicopter crashed, and unfortunately 16 people lost their lives. Unfortunately, down to the money. That's all it was. Just the procedure wasn't being followed to, unfortunately. The engineer had done the job correctly, but the company had made the helicopter fly. So unfortunately, a lot of people were killed for no reason at all. But again, that was a good few years ago now. So if you do pull a chip, you see something, highlight it straight away. Don't rub it on your overalls and say, oh no, it's going to cause me a lot of work, because if you do that, that potentially could cause an aircraft to crash. Okay, so make sure if you see something not normal, highlight it. It might be okay. You might just think, oh, it looks a different colour. Okay, but if in doubt, highlight it as soon as possible. Okay. Oil pumps, yeah, we need an oil pump. There's a breakdown of the gearbox. It's a very simple setup. You have various types of spur gears, various sizes, all with different ratios to rotate various components. Now, this is sort of the front of the gearbox. There's the back of the gearbox, and there you go. There's your bevel gear rotating to a shaft, which will go to your HP spool. Okay, attached to the gearbox, you've got aircraft generators. There's your centrifugal breather. Okay, so remember that's the one that expels the oil back to tank and allows the air and the oil to go to atmosphere. And you also have what's called a hand turn access. So you can actually put a tool in there, hand turn the gearbox, which will then hand turn your HP spool, so you can actually check compressors and turbines with the borescope equipment, or hand turn the engine from the hib button, etc. You have a starter to start the engine. Here's your oil pumps, and here now you can just about see, not the easiest thing to see here. There will be bigger gears compared to the smaller gears. So smaller gears would be the high pressure, and the larger gears would be your scavenger turn. Okay. You've got hydraulic pumps, low pressure fuel pump, fuel flow governors, okay, high pressure fuel pump. So again, all depends on the type of aircraft. The gearbox does quite a lot, but the main thing at the end of the day, it's there to start your engine. Okay. Again, in here there will be oil getting rotated around, so the engine oil will fill that up as well. So it's the same oil for the gearbox as it is for the engine. Okay, spread out by the pump itself. Okay. So basic pump, spur gear, as I saw before. All right, so you've got inlet from the oil tank, and should the case pressure build up too much, it will release back to LP. And high pressure side, if the high pressure system gets up too much, again, it will go back to the inside. That's just a basic poppet valve again, like we saw before. Basic spur gear. Oil coolers, we've already mentioned. Your FCOC, it could be an FCOC, it could be an ACOC, so fuel cooled or air cooled, but in our case, we're looking at the fuel cooled. So oil in between all the matrix, okay, these little thin tubes, you can just see there. So that's the fuel going in these little tubes, and going around the matrix of these little tubes is your oil. As I mentioned previously, there's your oil temperature transmitter, and there's your oil bypass. Okay, and remember, the PMV, the pressure maintaining valve, ensures that the oil pressure is always higher than the fuel pressure. You can see that these little thin tubes, yeah, they could potentially break down. The fuel going through them could be corrosive. It's been sat for a while. If one of those little tubes breaks, the fuel is going to come out. Well, that's not very good, but we can make sure by having the oil pressure higher, that will keep the fuel in there, and the oil might go into the tube and then go into the fuel. Well, that's not as bad as we saw before. Okay, oil into fuel can burn out through the exhaust. That's not so bad. Okay, so the basic oil cooler. There's your centrifugal breather. Okay, so there is attached to the gearbox by a drive here. So as it's spinning, the oil is coming in from the bearings. It gets spun centrifugally very, very fast. So the oil will get spun out towards the casing, it represented in green here, and that goes to the gearbox, and then eventually that'll stay there or go back to the tank. And then the air that's left will just escape out to the atmosphere. And occasionally you will get an odd little drip of oil. It's just the nature of it is. But most of the oil will go back to the gearbox. Okay, now we're going to move on to bearings. We've got various types of bearings to look at. So radial thrust bearings, all lots of good stuff. So different bearings for different jobs. Okay, because we've got the thrust of the shaft trying to escape out the engine. We've got radial action. We've got axial action. You've got one direction only, two directions. So a lot of different types of bearings. So what is a bearing? Well, it's a device for locating a shaft with maximum radial restriction and or axial restriction, but allows the greatest possible freedom of rotation. Very, very precision made bits of equipment. Obviously very crucial. You'll soon know if your bearing's getting worn. Again, going back to your cars, your motorbike, even your push bikes. If the bearing's getting worn, it gets notchy, it gets gritty. Again, it's bad enough on the ground, but in an aircraft, if you've got worn bearings, that could potentially lead to internal engine fires, which again, not very good. Ball bearings, they are divided into 4 main groups. And ball bearing, as it sounds, it's just a ball of steel in a cage. Radial bearings, angular contact bearings, thrust bearings, and finally instrument position bearings. We don't speak about these much, but just be aware of instrument position. These are smaller finite ones for gauges and that sort of thing, but you do get very small ones. The 3 main ones we'll look at are the radial, angular, and the thrust ones. Radial bearings, the most common type and found in all forms of transmission assembly, so gearboxes. Okay, so that's the main ones. And also you might find these in control rod ends and fittings as well. Okay, so in transmission gearbox type bearings. Angular contact, as it sounds, so angular contact. These accept radial loads, so centrifugal force. Also axial loads, so back and forward, but only in one direction only. And you can see that here. If you look at the cage that surrounds the bearing, the ball bearing, you'll see it's open one side, but it's got a lip on the other side. So you can make sure that when you fit these bearings, you put them in the right way around, or the ball bearing will just fall out. All right, so in this case, imagine the thrust would be going from this side to that side. It's going to try and pull the bearing that way. So it's in one direction. So it will accept the centrifugal force. It will also accept the linear axial force, but only in one direction. Hence why it's called angular contact. For axial loads in both directions, an opposed pair of bearings can be used. So if there was thrust going back and forward, you can spin one round and have a double bearing there. Thrust bearing. Thrust bearings only carry axial loads. So the thrust, so just think through the axis of the engine. So it's not to do with centrifugal force, although they are spinning. It is purely the thrust, hence through the axis of the engine. Normally used in conjunction with a roller bearing or a radial ball bearing. Okay, so axial load only. It's worth, when you're revising your bearings, make sure you understand that there's usually 2 or 3 questions, or at least 2 questions on a bearing. Make sure you know which one is which, but we'll recap these as we do revision. Roller bearings, I'm sure you've come across these plenty of time, may be divided into 3 main groups according to whether they have cylindrical, spherical, or tapered rollers. Okay, there's a classic tapered rollers. Again, if you've worked on cars, you've probably come across these in rear wheel cars, the rear wheel axis. Okay, packing the grease. Cylindrical ones, sort of smaller ones as well. We should call these sort of needle bearings. Okay, and the tapered ones. Again, they can be used for thrust loads on axis as well. So the roller bearings, stretch bearings. You know what I mean? So cylindrical roller bearings, again, they're capable of greater radial loads because they are longer, so they take more radial loads than similar small ball bearings. Okay, not so much thrust though; it's more for radial centrifugal forces. Some types will carry a light intermittent axial loads, but usually roller diameter and length are equal. Tapered roller bearings, these bearings, the axis of the rollers form an angle, hence why they're called tapered, with the shaft axis. So you can see the taper on the bearings there, yeah? Classic on cars as well. And they can accept simultaneous radial and also axial loads as well, but only in one direction. Okay, so in some of the old cars, you'd have 2 sets of bearings like this. I keep using the cars, just being ex-mechanic. Your outside bearing, the small part will be facing in the way, the large part towards the wheel, and on the inside bearing, it would be the small part facing you and the large part facing inside the car. So they'll be tapered one side. So as we've got there, okay, so this small side, this would be the outside near the wheel, and this side would be the inside near the hub, okay? And the same sort of thing for the actual wheels on undercarriages as well. These will all be packed with grease of the right quality, but again, for some of these, maybe some of the bearings and the gearboxes, etc. Ball bearings tend to be the ones for the engine shafts. All right. So that's a few different types of bearings. And then the last one we've got is what called is squeeze film bearing, and it is what it sounds. You squeeze a film of oil. Now there's the bearing there. Then there's the support, the cage that holds the bearing in. Again, you've got a cylindrical roller bearing there. And then obviously the bearing sits within a housing. Now to help prevent vibration, we squeeze a very thin film of oil between the outside of the bearing and the gap between the bearing and the housing it sits in the actual engine. Hence why it's called squeeze film. And the purpose is to help reduce vibration. Okay, so that's squeeze film bearing. Helps prevent vibration. If when you squeeze this bearing into the housing, you can imagine through heat and contraction, hot, it will expand, it will sit in nice and fit. But if it gets very cold, the bearing can contract and potentially leave a little bit of a gap. Now, if there's no oil there, when it starts up, it can chatter. Yeah, and that can cause a little bit of vibration. And eventually, it'd probably break down. So by putting a squeeze film there, that takes up any potential gap and allows it to monitor as normal. All that stuff with the engine oil system, there are plenty types of methods available for oil samples and be sent to analysis. I'm actually go down to a place in England which is called Kinetic, where it's a massive laboratory, and we send any samples of oil and fuel, and these laboratory technicians will sample, and they will tell exactly what is going on with the oil. If there's any suspect contamination through whatever, through fuel or whatever. This sort of kit, which is called a patch test kit, just for your own background information, we would get a sample of oil, dilute it with a special fluid, and then we get one of these little filters, put it in here, and we'd vacuum pump it through, and it would give a colour. And we have a chart which would be represented by this chart here, and depending on the colour, it would tell us exactly what was acceptable, what was not acceptable. We thought there was maybe some fuel in the system. It was basically like different greys, colours of greys and tans, and we could tell you what was wrong with it. Okay. Again, a specialist training before you use this equipment. But it's very simple. It only takes about 5-10 minutes to set up. The thing is, with these filters, they're very, very, very precise. You have to pick them up with a set of tweezers. If you touch them with your fingers, you can't use it because it's contaminated, even if your fingers are clean. Okay, it's very, very sensitive type filter material, but dead easy to use. Dead easy to use. Okay, so there's lots of different methods. This sort of system is called what is called a SOAP sample, which stands for Spectrometric Oil Analysis Program. Okay, so if you ever get here, I need to go and take a soap sample. It doesn't mean you can go wash your hands with some soap. It is a special way of testing the oil, as well as other parts as well. Again, we'll speak about this a bit more as we do some health monitoring. So in some cases, debris from chip detectors will also be sent away for laboratory or to an EFD centre. Now, usually big aircraft companies will have this on site. If they're really unsure what's going on, then yes, they will send this oil down to a specialist laboratory. But most big companies, airlines, will have this facility on site. Okay, specialist trained engineers like yourself, you guys can be trained up for this to do this as well. Okay, before we move on, any questions on the oil side before we move on to air side? Because I think there we go. It's 11:15. That's probably a good time to stop again for a quick break, and we'll crack on with the air sealing. So any questions before we go for another break? All good? Better than fuel system?
Yeah.
Good stuff. Okay, guys, go for another 20-minute break. We'll see you after then, okay? As you can see here, we'll get a small jet of oil going into the bearing, surrounds the bearing, and once it's done its job, it will return back to the scavenge line. Now, that's all very, very well. The oil comes in and it goes out. Now, if there's nothing to stop it going out the shaft, then it would just disappear at the shaft, front of the compressor, back of the turbine, and make a lot of mess and obviously potentially on fire as well. So what we do is we use various types of seals. I'll combine with air pressure, tap from the engine, to help keep the oil within the bearing housing. What we've got here is what's called an abradable lining, also known as a labyrinth seal. Now, it's a corrugated type seal. You can see here little ridges, and the line itself helps stop the oil coming out and allows the air pressure to keep the oil in. Because of the shape of it, you get sort of divergent type shape going on. You get high pressure, okay, from the air, so it helps keep it in as well. So it's working, again, back in the basic physics principle. So high pressure air both sides, that air pressure acts as a barrier, combined with the walls of the braidable lining, and keeps the oil within inside. Now, obviously, these are braidable. Now, what means by abradable is it's designed to wear. So eventually, these will wear out and have to get replaced at some point. It's metallic, abradable metallic lining. So again, when this starts to wear down, it can go into the oil system and back through your scavenge line, which will get picked up on your magnetic chips. So every time you open a magnetic chip, so many hours, you will see a lot of very fine particles of metal. And most of the time, what it is some of this abradable material, which is common, which is just standard. And the more experience you get, you'll recognise that as you take these out. You just say, yeah, it's abradable, but it still has to be analysed to make sure it's not part of the bearings, etc., or indeed the shaft. Okay, so we use the tapping of air pressure to keep the oil in along the shafts. And they come in various types and shapes and sizes, and these are just some examples. So again, there's the blue air coming in. There's your oil get pushed into the bearing, then go back to tank, etc. And if the bearing fails, then yes, you can potentially lose some oil at the front. Now, a good thing to watch out for is when you go to the front of your engine, you're having a quick inspection. If you see a big puddle of oil on the bottom of the intake, there's a good chance that these abradable seals or labyrinth seals have actually worn down. So when the engine shuts down, there's still a bit of pressure in oil because the gearbox is still spinning. So the oil pump's still spinning, providing oil flow. So eventually, if these have worn down and the air pressure's diminishing, then the oil can escape past the lab seals and then get down. So there's a good chance that if you see a lot of oil, it's probably worth checking to see how bad these lab seals are. Again, that will show up in your magnetic chips as well. They might decide, you know what, that's too much oil. That going back down the bypass is not very good, so they might have to do something about it. Okay, but they do come in various types, shapes and sizes, and that's always shown here, different shapes and sizes. Another type of air seal we've got is what's called a carbon brush seal, and it is, as it sounds, it's like a brush. It's very fine bristle, metallic bristles that are angled in one direction, so they go with the rotation of the shaft. If you go back the way, they can damage it. Now, if you're handling these ones, be very careful because they are like small needles. Okay, so they can get to your skin. Again, they will wear out eventually, but it's just a bristle type brush, one direction only to go with the shaft. So always try, if you're rotating an engine, always rotate the engine in the correct direction of rotation, because if you've got one of these fitted, if you go the wrong way, it can damage it. So always spin it the correct way. So again, just a different method of doing the same thing, forming a barrier for the air sealing. So in this case, we could have hot air here and normal tapping of cold air here, and that helps maintain a barrier. Air sealing, to maintain pressure difference, is a good one to note here. So to maintain pressure difference between two internal engine sections, we use not just one, we use a multi-air seal. This is a good one to highlight. There's usually some sort of question along this line, whichever way they word it. So depending on which part is in your old books as well, please make a highlight of this one and remember this one. So to maintain difference between two internals, so it's more than one, so it's plural, we use, nice and straightforward, a multi-air seal. And this gives an example of what's going on. Oops. You've got your nozzle guide vanes here, you've got your turbines, etc. So we've got air going on, we've got the HP cooling air, we've got hydraulic seals, we've got loads of different cooling air. Again, various types of lab seals as well. Again, on the back, there won't be oil going in there, but they will certainly have some sort of lab seal. So you're using multi-air seals to help join up with each one. Air systems themselves, well, we can take tappings of air systems as well as lots of things we can use, as well as the hot air to help cool the turbine blades, etc. You know, so we can use tapping from the back of the HP compressor, for example. That can be used for cooling the bearings and also for NGVs and turbine blades and that sort of thing. We've got the front bearing cooling from tapping of the LP compressor. So there's lots and lots of things. But eventually, we don't have to use it all. We can use some of it, internal cooling, external cooling, and then you can vent it out to atmosphere as required. So it all depends on the engine type. Okay, let's see. Now, you can see here, this engine we've got is a twin spool. So we'll just do a quick recap while we're here. Got a nice little diagram. So LP spool, 1, 2, 3, 4 stages. And the HP spool, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 stages. This happens to be a SPAY engine. I know that because I used to work on them. HP turbine, 2-stage, and an LP turbine, twin stage as well. And with a can annular type combustion system. So multi-can in a can, if that makes it easier to remember. Okay. So important design feature to ensure that certain parts of the engine and some accessories do not absorb heat from the gas stream. In other words, we keep the core heat within the core engine. We don't let that hot air go out towards the external part of the engine and indeed the fuselage, where it can potentially cause a fire hazard. So we can control the amount of cooling air etc. Because remember, the air from around here, it can be about, what, 500, 600 degrees, maybe 550 thereabouts. So again, we can tap that for the turbines, that's fine, but also it's already hot before it's going to combustion chamber. If some of that hot air escapes, then potentially that can cause a fire hazard in the cooler area of the actual engine. Okay. Let's see there's the NGVs, nozzle guide vanes. There's your turbine rotors. So again, we're using HP cooling air. So from back of your high pressure compressor, P3, coming up and through, and LP cooling air as well, okay, just to help maintain the roots of the blades. So by having the airflow of the NGVs and the blades, we find a boundary layer air, which means we can get those blades and NGVs to hotter, which makes the turbines, again, go back to what we spoke about yesterday, far more efficient. Okay. All right. Now, temperature monitoring, we've got to make sure we keep it in a certain area, a certain temperature. We've got the LP cooling flow, we've got the HP represented here by P3. And as I said before, there's a P3 back of HP compressor, combustion chambers, discharge nozzles, nozzle guide vanes, HP turbine discs, LP turbine discs, that's all very good. But we can also use LP cooling sealing flow for the front of the bearings, like we've got here. Fan bearing, HP compressor bearing, thrust bearing, more thrust bearings, LP bearings, support struts, etc. Well, that's all very well, but remember, it's also quite hot. You know, it can be 500, 600 degrees. Now, if there's a break in some of those pipes or something, and that hot air is escaping into the bypass side of things, which is getting closer to the external part of the engine, and indeed closer to the fuselage, we'll have an over-temp warning. There's some sort of thermocouple sensor which will give us a warning in the cockpit to say, wait a minute, we've got hot air where it shouldn't have hot air escaping. So they might have to shut that engine down. So it's all very good having all these tappings of air, but again, especially P3, if there's some of the hot air here escaping into this sort of section, then potentially that's going to cause an overheat situation and potential fire. Again, okay. All right, all good with that one. Engine bay, pod cooling, ventilation. We can cool the ventilator engine by compartment the air, drawing air from outside to inside just by Venturi action, as key here. So we get fast moving air in here. Just by ejector action, we can induce some cooler outside air, but that helps keep it cool, but also helps ventilate the area, because there could be bits of fumes from oil or fuel sitting about within that area, which also makes it very dangerous. So by venting the air out, by inducing air from outside into inside, we can vent it and purge any potential dangerous hazardous air out there. Oh, where are we going? Go back. Thought I lost you there. Okay, where'd that go? Thought we're going offline there. So yeah, by convection cooling, again, the hot air going out and the cooler coming in, we can, what we call is purging. Any potential fumes can be purged from there. All right. Oops. This perfect. A bit funny there. Now, these sort of grey areas here are described as fireproof bulkheads. Just in case a fire starts, we want to try and stop the fire from spreading where possible. We'll look at fire detection that later on, possibly today. So we put these into little zones. Hot zones, we've got electrical fire, potential electrical fires, and obviously fumes. If we don't vent it properly, can cause fires as well. So separate cool air zone of engine, which contains fuel, hydraulic systems, etc., and the hot area from the turbine and all that. We can use differential pressures. We'll have two zones and calibrated of the inlet and outlet ducts to prevent fire from spreading potential. So look at the zones. Okay, split them up to sort of three basic zones. You've got the front of the engine here, the back of the engine, zone 1 at the front, zone 3 at the rear. And it happens to be that where the gearbox is, usually within about zone 1, this is the most likely area of where a fire could start. Now you think, well, wait a minute, the combustion chamber and the turbine, that's the hottest part. Well, that's already on fire. But yes, that could escape sort of thing. But there's a good chance of mechanical hot fire because where all the electricals are, the fuel pumps, the hydraulic pumps, etc. So zone 1's a forward one, and zone 1's the most likely area to fire to start, as it's fit, and therefore it's fitted with the fire detection and remotely operated fire extinguishers. So to reduce the chance of a fire spreading in the zone, it's kept at a lower pressure than the other zones. So zone 2 is where the compressor blades may touch engine casing. So again, a heavy landing, the blades could touch the casing, cause a metallic fire. Indicated via engine vibration. Health monitoring systems are used. The zone is hotter than zone 1. Zone 3, again, is the hottest zone. Again, you would think, well, that should be the place that has a fire. But what will happen there, you've got the zone that's surrounded by an engine and jet pipe behind the combustion chambers, a fireproof bulkhead separates again from zone 1. All zones are also ventilated, so we can purge those zones out with a bit of help through ram air. And on the ground, when it is running, ventilation engine is achieved by inducers linked to the air system of the engine. We actually draw, but only effect on the ground, and we'll look at that just in a minute. We've also got a chance of any serious leakage of hot air to escape through a spring-loaded flap panel to atmosphere. Now, is it the previous one? I think it was. Yeah, there we go. This pressure relief door here. So if we only got any hot gases building up within that compartment zone, it's going to expand. Well, these are just simple spring-operated flaps. So if the pressure builds up, it'll open up there, and the hot air will escape out. So sort of self-sensing, self-operating itself. Okay. So zone 1, zone 2, and zone 3. Okay. And there you go. So a bit of diagram of where the zones are. So zone 1, zone 2, and zone 3. Okay. The cooling ventilation system, again, is more complex. Cooling is induced from the intake duct and also delivered from a fan to help produce multi-zone cooling. Again, the engine compartment, as I say, normally into 1, 2, and 3, and such like, and so we can help look after each compartment. Again, you'll have your fireproof bulkheads, so just in case there's a fire, the fire detection system will be activated, and up to pilot yourself to activate it as possible. But it helps prevent the fire spreading where it shouldn't be spreading, just in case. Drainage, well, we've got fumes, we've got potential leaks, so we need to have a facility for drainage. Some engines have a drain collector, some just open to atmosphere, like the old military aircraft IHUD. If we shut an engine down, we would physically have to go underneath the engine with a box. We put a pin through the box on the vent, then we get clear of the engine and give a signal to the pilot or the engineer to shut down the engine. And as you shut down the engine, any excess fuel would drain into that box, and we go and empty it into a proper container for disposal. Some engines, so to prevent that venting on the ground, they have a little collector, which then puts it back into the exhaust system, heats up and vaporizes. Okay, so in order to prevent possibility of fire with an engine, in cell ventilate to air is normal, but there's also potential for nothing going on here. Get this to move right. What's going on? The mouse has gone off funny. It's got a mind of its own. There we go. Potential for inflammable vapors to cause damage. So liquids lining the cowls need somewhere to drain away. So again, you have some sort of vents and etc. Again, separate oil tank where appropriate. Usually near the bottom of the engine, obviously. Components that are driven by the engine or its gearbox will have seals around the drive shafts, and that helps prevent internal liquids from escaping. Now, these seals, make a note of this one, or highlight it if you can on your old books until you get new books, are called gland seals. Okay, so seals around the shaft are called gland seals. So if one of those seals fails between the component, the attached structure, etc., the attached structure is called a web, and that will catch those leakages. Like a spider's web catches flies, we call this a web, and that catches the potential leakage. Okay, and pass through a drain at the bottom of the web. Top of the web will be vented to atmosphere, so we've got some expansion facility there, and force will force it through. And you have a drain at the bottom of the web, we'll have a pipe to safely duct away into the atmosphere. Now, you can use these drainage pipes to identify faults. Some aircraft have maybe all the drain pipes located together. It might be in line, might be 6 pipes. You'll have a diagram that number 1 pipe might be the fuel pump, number 2 pipe might be the HP pump, number 3 pipe might be something else, and that sort of thing. You can also have what's called wet drains and dry drains. It's not in the book, but just a bit of background for you. Wet drains, they're the ones designed to leak. So when you shut an engine down, yes, you might get a little bit of leakage out there, and that's normal. When you're running an engine, you might get occasional drip. Now that's fine as long as it's within limits. So if you're getting maybe 1 drip a minute, for example, in the book, I'm going to say that's fine. You maybe allowed up to 3 drips a minute. If it starts dripping more and more, that's indication that potentially that pump, let's say the fuel pump, is on its way out. I'll give you an example. Again, go back to the old cars. Water pumps have a indication drain that if you see water coming out the water pump and dripping out a water pump, that's probably telling you that the seal or the bearing has gone, and they're designed to do that before it totally breaks down. The housings at cracked, there's a proper drain hole there. That's to give you indication, and that's called a dry drain. And some aircraft have the same. You might have 3 wet drains and 3 dry drains. If you see a drip coming out a drain pipe, which is classed as a dry drain, well, it shouldn't be dripping. So that's an indication there's internal failure of whichever component that drain is attached to. Again, you'll learn about these on the type of aircraft you work on. We'll have a drain valve there as well, obviously to help drain stuff off into a suitable container. Some of them go back into their own tanks. Sometimes they go back into the system. So by determining the pipe that is leaking, it's coming from, then just shut down again by an HP cock. Will allow the fuel in the burner and manifold to vent to atmosphere, and the other side of the fuel and the compressor delivery pressure, the fuel will be forced out to the burners and off the atmosphere, and the purged fuel is collected in a drain tank situated at the bottom of the engine. The tank is used to prevent any loose flying on the ground and vaporising, because it's quite high, it's obviously quite warm and vaporised, so potential fire hazard. And again, if that was to happen, good fire hazard, potentially ignite. Okay, so it's not so good. We don't want that. So here's a typical collector. This is actually on a 211 engine, one of the old Rolls-Royce ones. So it'll collect there, and you'll have a drain point. You can actually drain it. So the drain tank itself, fuel's drained, sometimes emptied during the next start cycle, so it'll go back and into the exhaust. Okay, creates a depression and allows it to go to atmosphere pressure and push the fuel out of the drain into exhaust, and it will hopefully ignite with that as well. There's not usually too much in there. All right. Other types, you might have generally more modern engines. The drain tank is emptied by a fuel flow from a post-LP pump source to the ejector pump and at the bottom of the drain tank, and then passes off the inlet to the LP fuel pump. So it gets reused again, it gets burnt off, so it's quite good. So this is actually the one we've got in the hangar. Okay. And probably hard to see in the page there, in the books, well, certain new books, this gives you examples of some of the wet drains, limitations. Again, you don't need to remember these are just pure examples. So we'll just pick one at random. So there's the fuel pump assembly. Okay, so fuel. If the engine is running, it tells me I'm allowed 10 drops per minute, or 30 cc's an hour. If the engine is not running, you're allowed 7 drops a minute. Okay, if it's not running, it shouldn't be as many drops. Pick another one, for example, a hydraulic pump. Hydraulic oil, 5 drops a minute. Engine oil, 1 drop in 3, which is pretty common. That's quite a common one. Okay, and various other ones. Some of the notes in there: if engine static, the fuel leak check is exceed engine running at fuel leak check. Maximum engine running leak check of 300 cc's an hour. Again, this is just an example taken from one type of aircraft. Your type you work on will be specific to your one. Okay. So if you see something dripping out a drain, make sure it's a normal drain. If it's meant to be dripping, if it's a dry drain and it should be dripping, well, that's probably a fault. But go and check how many drips you are allowed as it's running and static. I'll briefly mention accessory cooling, where obviously when the aircraft's flying, it's getting nice cool air on the outside, keeps the aircraft cool on the outside, and obviously the engine as well. But if you're ground running or doing performance run on the ground, you need to induce some cooling air to help keep it from overheating. So a considerable amount of heat is produced on some accessories, your generators, for example, they get warm very quickly and often require some own cooling. So air is sometimes ducted in from the intake louvers, or the gaps there, into the engine cowlings, or it may be taken from a stage of a compressor to help keep it cool. So when things going off again. So an accessory is cooled in flight. Atmospheric air pressure is passing through the louvers, the little segregations in the cowlings, and again on the ground we need to induce a flow. There's no external airflow, and that's achieved by allowing a tapping from the compressor, deliver the air to pass through an air duct to the actual accessory itself. Now the speed through the nozzles creates a low pressure area. Okay, so high moving gas, so it means it's low pressure. So by that low pressure, it will attract atmospheric pressure into it. Okay, now these are only operated on the ground, so you can't activate it in the air because, well, there's no need to. You've got nice cool air. So ensure the ejector only operates on the ground. The flow of air from the compressor is controlled by a pressure control valve, which is only available to be activated when the aircraft's on the ground. In other words, when you've got your weight on wheel switch. Okay, so as soon as that disengages, it will isolate that system. You don't need it, you're flying, you've got forward movement, you've got a cooling airflow you can induct into the actual aircraft engine compartment. Engine off-takes, yeah, you use a lot of off-takes to do lots of things. So in any aircraft, piston engine as well, there's gas turbines, there's also a need for many accessory systems that need power to them. So you've got hydraulic pumps, generators, magnetos, RPM, etc. So there's quite a lot of things we can actually fit onto it. Now, gas turbine engines usually fly much higher than piston engines, so that at high altitudes where pressurization and air conditioning are a must. We've got to try and recreate ground conditions way up at 30, 40,000 feet. So we need to pressurize it, and we also need to increase temperature as well, air conditioning. Otherwise, it's going to be very cold and unable to breathe up there. Okay, so false tapping high pressure air from various stages of the compressor. And air is not only for air conditioning and pressurization, but it can be used, like we saw, for anti-icing. Okay, so we're putting the hot air back into the engine to prevent ice building up. It can also be used for head of tank pressurization of the fuel system, and some air compressor airs is used for self-contained engine starting systems as well, and also for boundary layer air on takeoff and control. Some of the old aircraft would actually induce airflow over the wings for boundary layer control. Certainly one of the old aircraft, the Buccaneers I used to work on, they used to have a boundary air layer. They actually blow air over the wings to help them fly a bit better. Okay, and this is just an example of lots of things you might do tappings of. Okay, again, just an example. Okay. So mechanical off-takes. Well, we've got the big gearbox. We need the gearbox to spin the engine. So you'll definitely have a shaft. Well, here we go. There's your high-speed gearbox. There's your bevel gear and the shaft, which should go off to your HP spool. Again, you've got some spur gears, but helical gears now. Spur gears are direct gears. Yeah, they just mesh like that. They're quite noisy. To get smoother, more powerful operation, we'll use what's called helical gears, which I showed you earlier on. Again, there's a centrifugal breather, starter mounts, auxiliary gearboxes, some straight cut gears, front casings, and so on and so on. Okay, so there's lots and lots of different things that can be attached to there. The arrangement of gearing will determine the RPM of the accessories on the engine speed. So some of the gears will be larger or smaller depending how fast they are to rotate. And certainly if you've got an RPM gauge, a tachogeny as we call it, this is proportional to engine speed. So your RPM gauge, your tachogeny is proportional to engine speed, and we'll look at that later on. Air off-takes, yeah, we need to use some air, we saw already. Normally controlled by an electrical on-off valve, simple solenoid operated valve. Because of the high temperature of the air sliding valve, the valve is usually made from a carbon type material. When the aircraft is self-contained air starting system to start its own engines, you'll have additional pipework and valves fitted as well. Just a simple solenoid activated carbon encased valve. Okay. Now again, you use tappings of air for lots of things. Now one of the ones we're going to look at here is what's called active clearance control, or ACC. All this is doing is obviously as the rotors, the compressor and the turbines go around within the casing, at the tip of the blade to the casing is a little gap, which obviously has to be there. If there was no gap, it would rotate. But if that gap gets too much or too small, that can affect performance of the engine. Now with FADEC controlled engines, they will maintain the gap by using airflow, as in to cool or allow the blades or the casing to heat up or contract to maintain that tolerance of the gap. Because if you heat something, it expands. Well, engine casing is going to expand, the blades will expand. So by using airflow control, we can control the temperature of the casing and the blades to maintain that perfect gap. So as said there, air loss across the tips of the rotor blades of an axial flow compressor and across the turbine blades will reduce the efficiency. The bigger the gap, the less efficient it is. Okay, and the losses occur between the clearances, as I said before. So we need to somehow control the gap on them. Now, you've got centrifugal loads, you've got engine temperature, different expansion rates of different materials. Again, different forms of gas leakage across the tips of the compressor and the rotor. So to overcome that, the air gap must be use a few methods, and this is what we use as active clearance control. Again, controlled by FEDEC. It'll use different stages of compressor air as what's called a thermal medium. So using the heat, depend what heat of the air we use, will depend the expansion or contraction of the casings. And that's pretty much what it does. It expands and contracts between the casings and the blade tips, and they provide to make it fully efficient. As I said already, ACC is controlled by FEDEC, so FEDEC is in charge of everything. It's controlling the fuel, it's controlling the airflow control, it's controlling absolutely anything, okay? And it will measure the tip. There'll be sensors there to measure the gap between the tips and the casings, okay, between the shroud ring and the compressor rotor, and it will cause dimensional changes to maintain it by increasing the heat or decreasing it accordingly, depending on what's happening with the engine. Okay, so that's ACC for compressor blades and rotor turbine blades as well. Then we've got an action of that one. In fact, before we move on, with the diagram we've got there, we've got LPT and HPT ACC, okay, active clearance control, and I'll come on to that in a minute, but just remember that diagram. What we'll show you is these rings around here, this is where the tapping of air goes. So the air will go into these rings, and it'll be hotter or cooler as required, which will then act as a heater to expand or contract the casings, in this case the turbine in this one. The rotor active clearance control is purely for the compressor only. Okay, so it will vent hot air or whatever to the casing. I can just about see some of the tappings here from there. Okay, so compressor only. So involves controlling the expansion of the compressor rotor only. So ACC is compressor rotor and the turbine. Rotor active clearance control, as it sounds, is rotor. It is purely for the compressor, but pretty much the same effect. Again, controlled by FEDEC, a valve operated, hydraulic by fuel pressure to deliver the air mixture compressor. FEDEC system measures again clearance. If outside, it will generate a signal error, okay, which will operate the mixer valve, which will then direct the required mix of air to the interior of the rotor. Okay, so that's the interior of the rotor. That will mix there. The temperature there will cause the rotor dimensions to change and restore maximum tip clearance. So basically, this time, instead of the casings being controlled, it's the actual rotor. So by inducing hot or cold air within the compressor, the blades themselves will expand or contract. Okay, so that's the two types. They're very similar sort of things, ACC and RCC. Okay, and along with that one, we've got what's called high pressure turbine active clearance control, or HPT ACC, and low pressure turbine active clearance control, LPT or ACC. Now this one is purely for the turbine section. So HPT and LPT ACC is purely for the turbine only. Okay, and like we saw in that previous diagram, just go back to the previous diagram there. Oh, that one there. There you go. LPT and HPT ACC. Lots of abbreviations. So there's your rings that will expand the turbine blades only. Okay. So that picture, I need to move that to the next slide, to be honest. Turbine only. Okay, so that's active rotor clearance control, or ACC. They're all active clearance control, either for both turbine and compressor, or just rotor only, or just turbine only. Okay, it's all it is maintaining the clearance of the turbine tips and the compressor tips to the shrouds and containment rings to make sure the most efficient angle as possible. Too big a gap means too much gas loss, which will become inefficient. Too small a gap, well, potentially it could actually hit the casing and also become inefficient. All right, what are we doing for time there? Right, that takes up to engine starting systems. We'll start this after lunch. What I'll do is do a quick 5-minute recap on some parts. and that'll do up until lunchtime, so tea time. Okay. Everybody okay so far? Anybody lost the plot yet? All good so far?
Okay.
It's okay. Happy smell face. Good man, Pasmani. Good man. Right, let's go back the way as we normally do, in reverse order. No point starting the starting system, no pun intended. Okay.
करो यार.
Put your volume down. Thank you. Right, okay. We've got zones 1, 2, and 3. Which zone is most likely to have a fire? Anybody? Well, yeah, it's zone 1. Yeah, that's a zone 1. We've got the gearbox. So yeah, that's got to elect all your pumps and that sort of thing. Although it's not the hottest zone, it's most likely to have a fire. So we have the fire wire and all that there, which we'll cover probably later on today. Okay, good. Temperature monitoring. So we're using bypass air, using tapping of air for compressors, HV compressors, LP compressors. How do we find out, or what gives an indication that potentially maybe hot air is going where it shouldn't be going? You know, where would it be fitted? So say we've got P3 cooling air, which is very hot, and it starts escaping. How do we know it's escaping?
LP cooling air outlet duct.
Yeah, there'll be a good, thank you here. There'll be a temperature sensor, thermocouple, some sort of heat sensor, and the LP cooling outlet. There'll be normal temperature in there anyway, and that'll be monitored by a separate sensor. But yeah, if that gets too hot, and it shouldn't be getting too hot, then there's maybe something's cracked, maybe a turbine casing's cracked, or a pipe's cracked, or something. You know, it lets us know that in the cooling air, it's gotten too hot, something's wrong. Potentially stop a fire from happening. Okay. If we were to mean the pressure between two internal engine sections that are subject to air pressures of a different value, what type of air seal would we use? So maintain the pressure difference between two internal engine sections. What type of air seal would we use?
Multi-air seal.
Yeah, simple as that. There's two different sections, so it's multiple. So multi-air seal. Nice and straightforward there. Good. Okay. What do we call another name for the abradable seal that has air on one side and oil on the other side? There's a little abradable seal. It's called abradable, but it's also another name. In Greek mythology, if it helps.
Squeeze flame.
Say again?
Squeeze flame, maybe.
No.
Carbon cross seal.
Labyrinth seal, yeah. Taken from the Greek mythology, labyrinth. Okay. Shorthand, we call it a lab seal. Just for short, it's a lab seal, but it's a full name's a labyrinth seal.
Sir.
Yeah. A labyrinth seal.
67.
Yeah, 67 on this page. Have you got new books?
No, sir.
Not yet.
Oh, all right. Oh,
They
well,
won't give, I guess.
well, this is page 67. Or using it on the PDF for you? Because this is the new book, and that's page 67, yeah. Sorry, not 67. This is actually page 69, a new book. So it's not far off, not far off. I thought you may have got new books there. Hopefully you get them by the end of the week with a bit of luck. Okay, bearings. We've got squeeze film lubrication. How does that work? Squeeze film lubrication. What does it prevent?
Pardon, sir?
What does squeeze film lubrication help prevent?
Minimize the dynamic load.
Yeah. Dynamic load, reduce vibration. Yeah. Good, good, good. Okay, and last one before we go for lunch is which type of bearing accepts radial and axial loads but only in one direction?
Angular contact bearing.
Angular
Angular
contact.
bearings. Thank you very much. Okay, good. Right, that's bang on 12:15 there. Well, my time. So what's that? Is that 6 o'clock out there, is it?
Yeah.
6
Yeah.
o'clock.
Yes, sir.
That's time for my lunch and your tea. Or your dinner, whatever you call it. Okay, guys.